Welcome to one more lecture on subRiemannian geometry. I previously introduced a result on limits of Carnot-Karateodori spaces. Now we can either see more consequences of it or discuss the proof of that result. Actually, I would like to see an example of the result. Maybe a concrete example where we can see the validity of Pansu's theorem. Okay, then for a better understanding of Pansu's theorem, I will now show a simple version of it. We shall prove that the asymptotic cone of the Riemannian Heisenberg group is the subRiemannian Heisenberg group. Because this Lie group has nilpotency step 2, there will be some simplifications. However, some of the arguments will resemble the strategy in the proof of the theorem about limits of Carnot-Karateodori structures. Happy? Okay, good, thanks. Okay, so let's discuss the Riemannian Heisenberg group and its asymptotic cone. Okay, so what is the setting? So the setting is we have R3 with 3 vectors that are left invariant with respect to some group structure, and the Lie algebra structure has 3 vectors x, y, z. So this is be a basis of the Lie algebra of the Heisenberg group. With only relation, bracket relation, x bracket y equal to z. And we defined a Riemannian metric declaring these 3 vectors orthonormal. So let D1 be the Riemannian distance associated to the Riemannian structure for which the vectors x, y, and z are orthonormal at every point. Okay, let's give a name also to the group, which is the Heisenberg group. Let's call the Heisenberg group G. Okay, so now we want to study the asymptotic cone. So we want to study the asymptotic cone of GD1. To study the asymptotic cone of a space, what we have to do, we have to shrink the distance by multiplying the distance by a number that is very, very small. Okay, so it means that we take lambda, or call it epsilon, so a small number, and we consider the distance lambda d1, and we want to take the limit Gromov-Hausdorff sense of the space G lambda d1. Now, when you have a Riemannian or also subRiemannian distance, it's easy to dilate the distance in terms of the Riemannian structure, because if the distance d1 has orthonormal frame, the vector x, y, z, Then, what is an orthonormal frame for this new distance? I claim that the distance lambda d1 is still a Riemannian distance, with respect to the frame, the orthonormal frame, the frame that is declared to be orthonormal, and now it's 1 over lambda x, 1 over lambda y, and 1 over lambda z. So let's see if I'm correct. So, lambda is a small number, so this is a very long vector. And indeed, now this in the new distance, the new Riemannian distance, this should be a unit vector, because with following it is going to have a unit length in the new distance. Okay, so it's correct. Just check that declaring these three vectors an orthonormal frame, we get a distance that is exactly equal to lambda d1. Okay. But let's pay attention, because, okay, now we cannot just take the limit of these vectors, because, of course, these vectors will just blow up. So we cannot pass to a distance in the in these coordinates. Okay? So let's change coordinates. What we do, we change now change coordinates. Using the map delta lambda. So delta lambda now we see as a map from R3 to R3 that as a matrix is the matrix lambda, lambda, lambda square. Okay. So what we know is that in the coordinate of the Heisenberg group, this map is a group morphism. Now, of course, I'm writing R3 because I'm considering exponential coordinates. Okay, so now what I will do, I will consider other coordinates, so other vectors. So consider the vectors x with depending on lambda to be delta lambda of 1 over lambda x, y lambda to be delta lambda 1 over lambda y, and z lambda to be delta lambda of 1 over lambda z. Now you see what I did, I changed using coordinates, this linear map, those three vector fields that we had before. So it means that if we take these three vectors and declare them orthonormal, we obtain the distance lambda d1. So the Riemannian distance making these three vectors orthonormal is isometric via delta lambda to the distance lambda d1. Okay, so we have another model for our space. Now these vectors, because of the map delta lambda, are much nicer than the previous one, because remember, so delta lambda multiply x by lambda, so this means that x lambda is actually x, likewise y lambda is y. And now what happens to z? So this map multiplies by lambda square the vector z. Okay, so we multiply by lambda square and divide by lambda, and what we have is therefore lambda square divided by lambda, so lambda z. Okay, good. So now we have a frame in R3 that is giving the distance that we want to study. And moreover, now, when lambda goes to 0, this vector just goes to 0. And so the limit is a bracket generating distribution. And you see, what we are having is a sequence of Riemannian structures converging to a sub-Riemannian structure. Okay, so I'll make you notice that x lambda converges to x because it's actually constantly equal to x lambda y to y, and z lambda instead converge to 0 as lambda goes to 0. Okay, so call d lambda the Riemannian distance for which x lambda, y lambda, and z lambda are orthonormal. Then the Heisenberg group, or R3 with d lambda, is isometric to R3 lambda d1 via the map delta lambda. So now what we are going to study, so our claim is going to be that R3 with distance d lambda converges in the Gromov-Hausdorff sense to R3 with the Carnot-Karateodori distance of the Heisenberg group. Okay, this will actually prove two things. One is that the subRiemannian distance is a limit of Riemannian distances, and also because of this fact will tell us that the subRiemannian Heisenberg group is the asymptotic cone of the Riemannian Heisenberg group. And the way we will prove this this convergence is using one of those criterion that we mentioned in previous videos. We will really prove that this distance, the lambda, converge uniformly on compact sets to the distance dcc. Okay, so actually d lambda minus dcc, or goes to 0 uniformly on compact sets of R3. Okay, so let's prove it. So which means, i.e. for all, we can take balls as compact sets for all radius r. There exists a sequence epsilon lambda going to 0 as lambda goes to 0, such that for all points P and Q in the Carnot-Karateodori ball of radius r, okay, we can take it a closed ball, the open ball, doesn't matter. For all points, what we have is that the distance dcc between P and Q is less or equal than the distance d lambda pq plus epsilon lambda, and is greater than, actually I'm going to write something stronger, d lambda pq, and I'm not going to write anything, I'm not going to write epsilon n, okay? Because actually I'm going to prove something a little bit stronger. I mean, you will see that this inequality is actually very easy. Okay, so we shall prove this inequality. Okay, so let's start with the first inequality, which is easy. So the proof. Okay, So the fact that actually d lambda is always smaller than dc is clear, since every horizontal curve, every curve that is defining every curve is defining this distance is of course a horizontal curve also for the subRiemannian distance, and the length is exactly the same. But here we have more curve infimizing. So every horizontal curve for DCC has exactly the same length for d lambda, because remember d lambda had x, y, and lambda z, right? So and instead in DCC we consider curves tangent to x and y, and see the length stays exactly the same. See, the length for curves tangent to x and y is exactly is not depending on lambda. Okay, so this first inequality is proved, okay, really globally. Okay, for the other inequality. For the other inequality, okay, so let's take points. Take P and Q in B, C, C, ball of radius R, and let gamma n from gamma from no, it will depend on lambda, from 0, 1 into the group G or R3, be a curve, a geodesic for the distance d lambda between P and Q. Namely, the distance between P and Q is equal to the length respect to d lambda of the curve gamma. It's a distance d lambda, which means that this is we can write, so gamma has to be a curve, gamma dot is a curve, and it's so we are Riemannian distance. So we can decompose the derivative as a function a1 t, so d1 t of x at gamma t plus b, no, a2 t y at gamma t plus a3 t z at gamma t. Okay, now what is the length? The length of this curve is the integral between 0 and 1 of the square root of, so x1 and y1 have length 1, so this is a1 square plus a2 square. But now z does not have length 1. Z has length, so this is length 1, so z has length 1 over lambda. So this is plus a3 square over lambda integrated. So this is the length of the gamma. Okay. Now, okay. Now we have to bound the distance, the subRiemannian distance between P and Q. What we do, we consider a curve that has more or less the same tangent, but just the horizontal part is the same. So what we do is let sigma from 0, 1 to R3 be the curve, be a horizontal curve such that, so starts at P and its derivative at time t is equal to a1t x sigma t plus a2y at sigma t. We consider this curve, okay? It's easy to verify that this ODE has a solution. Okay, but now what is the picture that we have? Let's draw a picture. So we have P, we have Q, and then we have the geodesic gamma lambda for the distance d lambda. Okay. Now what we did, we consider a curve that has the same part of same derivative with respect to x and y in the direction of x and y, and this is going to be another curve. Right? This is called curve sigma. Sigma has by construction the same initial point, but the final point is going to be different. Okay, so this is, let's call it q bar. This is by definition sigma of 1. Okay, so let q bar to be sigma at 1. So this is another point. Now what we need to do, we want to so this sigma actually has length less than gamma. This is easy to check, but now we want to estimate the distance, the Carnot-Rateodori distance between q and q bar. Okay, so what we do now, will be easy to really construct a curve that is vertical. So we do like this. So let eta from 0, 1 to R3, the curve such that sigma 0 is q bar, so this direction, and sigma dot at t is equal a3t z eta t. Namely, it's in this we took this curve and we consider a curve with these two controls, and we call it sigma, and then another curve with respect to these vectors. And then we took another curve that with respect to this vector as this control. Okay, and so this is going to be the curve eta. Okay, now let's make a claim about the curve eta. So I claim the following. I claim that eta, I mean, I really want to say that this curve is the vertical curve here, and this is nothing else than really how much these two curves they differ at each time. Okay, so I write it like this: eta of t is, so consider gamma t, the point here, then left translate by sigma t, and then bring it to gamma bar. So it's like this. So this is sigma t minus 1 and times q bar. So these are products in the group law. Okay, I claim that this is, we have this equality here for all t. Okay, now let's check that I'm right. So first of all, when we evaluate at 0, so we have gamma 0, sigma 0, q bar. Now this is q bar. Sigma 0 was p, gamma 0 was p, so we have gamma bar. So also this curve at 0 is equal to this point, like eta. Now let's verify that this curve as a function of t also satisfies this differential equation. Okay, so now what we want to prove is that the derivative of this other curve, q bar sigma t minus 1 gamma t, is equal to the derivative of eta, which means a3. So is it equal to a3z of at the correct point? So we want to prove this inequality. So it's good of the Heisenberg group that we really can express this product. Okay, so let's calculate the product. We calculate. Actually, we can really calculate sigma and gamma, sigma, and the product. So first of all, what is gamma? Gamma was such that it was a1x plus a2x plus a3z. And now let's take, so x is 1, 0 minus y over 2, y is 0, 1 minus plus x over 2, and z is equal to 1, 0, 1. Okay, so now put from this equation we can calculate, and we get that gamma is equal. So integrate. So let's do it slowly. Gamma dot is equal to a1, a2, then there is a3 minus gamma 2. So gamma 2 is the second component, is the y of gamma. Gamma 2 over 2 a1 plus gamma 1 over 2 a2. So this is gamma. Likewise, we have that sigma dot instead does not have this a3 part. Okay, so it's a1, a2 minus gamma 2 half a1 plus gamma 1 half a2. Okay. Now we can integrate them, or maybe it's not necessary to integrate them immediately. What we have is the following. So gamma 1, the first component, was just is the initial point. Okay, was p1, the first coordinate of p, plus the integral from 1 to t, this is gamma t, p1 of a1. And this is likewise for sigma 1. And gamma 2 t is equal to sigma 2 t is equal to integral to the p2 plus the integral from 0 to t of a2. Okay. Now we are ready to calculate this product here. Okay, so what we have is that sigma t minus 1 gamma t. This is the group, the group law of the Heisenberg group in exponential coordinate is the following: gamma 1 minus sigma 1, gamma 2 minus sigma 2, and then there is gamma 3 minus sigma 3, minus 1/2 of sigma 1 gamma 2 minus sigma 2 gamma 1. Yeah, I change sign because of this minus. Okay, so this should be the product. Now, as we said, these two are the same. So this is 0, 0. And so what we have, and also gamma 2 is equal to sigma 2. and sigma 1 is equal to gamma 1. So this is also 0. So what we have is 0, 0, gamma 3 minus sigma 3. Okay? So now if we have to calculate the differential, okay, we multiply by, we left translate, but we don't care because this is a left invariant vector field. So up to left translation, what we have is that the derivative in time of sigma t minus 1, let's put q bar sigma t minus 1 gamma t is equal to the left translation, or the differential of the left translation of the vector 0, 0, gamma dot 3 minus sigma dot 3, which by construction, I mean, the difference in this derivative was exactly the vector, the difference between gamma and sigma in the third coordinate was exactly, sorry, the difference between gamma dot and sigma dot, it's equal to A3. This is the only difference that they have. So this is equal to gamma star A3, or 0, 0, A3, 0, 0, A3, which is what we wanted. So this means that what we concluded is that sigma t eta t, sorry, coincide with the curve gamma bar sigma t minus 1 gamma t. Okay, let's see what we can deduce from this formula now. So what we deduce is the following. So for time t equal to 1, we deduce that we have that eta 1 is equal to q bar sigma 1 minus 1 gamma 1. So sigma 1 was by definition was equal to q bar. So this is the identity, and this was p. In other words, the picture that I drew before was correct. So we had gamma, we have sigma, and then the curve eta starts at this point q bar and really ends at the same point p. So now we got a triangle. And this will help us in estimating the distance between p, sorry, this was, no, so it was not, I wrote it wrong. This is q, this point is q, this is p. So now we can estimate the distance between p and q passing via q bar. Okay, so let's bound the distance between p and q. How can we do that? So before estimating the distance d lambda or dcc between q and q bar, let's see what they are doing in coordinates, like from the Euclidean point of view. Namely, I really want to prove that as eta, as lambda goes to 0, this q bar converge to q. And let's see if it is true. So let's estimate. So what is the length? The length, or the Euclidean length of eta. Or the Riemannian length. Let's use the distance d1, the d1 length of eta. So to get some kind of bound, we have to consider the fact that p and q have subRiemannian distance at most r. They were in the, or 2r, right? They were in the, because they were in the ball of reduced r at the identity. Okay, so let's use this fact. So what we have is that so the distance, the cc, the Carnot-Theodore distance between p and q this is less than 2r. This was because P and Q were in the ball of radius r, CC ball of radius r. Now, the CC distance, as we said, is greater or equal than the d lambda distance between P and Q. And since we chose gamma to be a geodesic, this was equal to the length respect to d lambda of the curve gamma. And as we said, this was equal to the integral of the norm of A3 A1x plus, let's write as we said, as we wrote it well before. So this was equal to the square root of A1 square plus A2 square plus, how did we write it? We wrote it here. But here there is a mistake. This cannot be lambda. Of course, because here one has to put the norm square of z. So let me correct. Hope you're following. So here we have to put a square. Okay, here. So now it's correct. Sorry about this. So let's correct. Let's write. So now this is going to be A3 square over lambda square integrated between 0 and 1. And of course, this integral is greater or equal than just the integral between 0 and 1 of the norm of A3 divided by lambda. So what we get is that, okay, we get this, this bound, that this number here is less or equal than this one. So maybe let's write it as the integral between 0 and 1 of A3 is less or equal than 2r lambda. Okay, so now this will help us in estimating the length of eta. Now then, the L1 length of eta, or maybe what we actually want to bound was the distance between Q and Q bar, which is less than the length of eta. So this is the integral of A3z. So this is the norm respect to the first scalar product, lambda for lambda equal to 1, and which is exactly the integral between 0 and 1 of norm of A3, which we said is less or equal than 2r lambda. And this number goes to 0 as lambda goes to 0. R is fixed. Okay? Therefore, what we get that these two numbers, these 2 points are converging to each other. Okay? So and therefore, what we can use the ball box theorem. So eta bar is converging to eta, and for lambda small enough, we can bound. So by the ball box theorem for the Heisenberg group, for the subRiemannian Heisenberg group, we have that the CC distance between Q bar and Q is less or equal a constant, which actually we calculated, d1 between Q bar and Q to the power 1/2. And as we said, this is less or equal than k square root of 2r lambda. Okay, we are ready to conclude, because now what we have that the distance, the CC distance between P and Q, which is what we want to finally found, this by triangle inequality, this is less than PQ bar plus distance from Q bar and Q. Now, the first, this one, we have a horizontal curve between Q and Q bar, which is sigma. So this is less than the length, the CC length of sigma. And the other one, so from above we have this big O of square root of lambda. Now, the CC length of sigma by construction is less than the lambda distance, the lambda length of gamma, which was equal to the lambda distance of P and Q. So we also proved the other inequality for the distance. So we finally proved that the distance d lambda converge uniformly on compact sets to the distance d lambda. If you like the video, you can let me know by clicking the like button. This will also suggest the course to other people. If you want to see more videos on subRiemannian geometry, please subscribe to the channel clicking below. Bye.